Welcome to Study Loop.
Here we have a small resistor mystery to solve. So there are two packages. One has two resistors in series, and the other one has the exact same two resistors in parallel. So we are going to have to use the experiment with a battery and measurement of power on the packages in order to figure out those resistors. So what we'll need are a couple equations for power. It is either delta V squared over R. An alternative using Ohm's law is I squared times R equals power. We'll also need the equation for series resistance. Our series is R1 plus R2. And parallel resistance is, we'll write it in the inverse, 1 over R1 plus 1 over R2 is 1 over the parallel resistance. So we need to set up two equations. The delta V squared over R equation will be sufficient for both these circuits for now. In the first equation, we set the known power in the series circuit equal to the known voltage of 48 volts squared over R series. And we solve for the R series by cross multiplying is just 48 in ohms. The second equation, we do the same thing with the R parallel. The power is equal to the voltage squared divided by the parallel R parallel resistance. And we find that the parallel resistance is 9, again in ohms. But these are going to lead to two equations that we can then solve for our two resistors. So we know that R1 plus R2 now has to equal 48, and 1 over 9 has to equal 1 over R1 plus 1 over R2. I will outline the algebra and show some intermediate steps, maybe not all of them. So these are two equations in two unknowns. They are a little bit nonlinear, but you can go about solving them the same way you would linear equations. So we're going to take the first equation and use it to solve for R2. And then we will sub R2 into equation 2. What that will do is equation 2 can be algebraically manipulated until it becomes a single equation in one unknown that can be solved for. And when you do that, you wind up with a quadratic equation in R1. So that's a little bit awkward, but not terrible. And I will show that quadratic equation. I won't go through the details of using the quadratic formula, but we basically have R1 squared minus 48 R1 plus 48 times 9 is equal to 0. And that has a solution. R1 is 24 plus or minus 12 ohms. And what that means in terms of the solution for R2. So we can sub this back. Now, it's helpful to know which resistor is which. So I am going to make the bold assumption that can be confirmed by someone else that R1 is greater than R2. Okay, so we will assume that someone has given you that information. Then we know that R1 is the plus solution. And then R2 is 48 minus 36, or the 12 ohm solution. So, yeah, those two solutions have to crop up from the solving of the equation, and they do. So now let's see who's the culprit in each circuit. Which resistor draws more power in each circuit? And this can be answered just with our power formulas. Power is equal to delta V squared over R, can be used to deduce which resistor in the parallel circuit. Remember, parallel means same voltage across the two resistors. So in the parallel circuit, it is the smaller resistor, or R2, draws more power. And we can do the same analysis with power equals I squared times R for the series circuit. Series means that it's the same current through the two resistors. And we can see from this formula that the larger resistor draws more power. Yeah. So interesting mystery solved.